So thank you for this invitation. I thought I would sort of give you at least my sort of perspectives, I guess, and what we're working on, and talk about neuromorphic algorithms and how do we figure out how well they work on realistic neuromorphic substrates. And part of this work is things I was hoping some other folks would have done by now, but it's been a while, so I figured we would need to chip in as well. So just to give you some background, my actual background is on chip design. We work on asynchronous chips. Neuromorphic chips just turns out work well with asynchronous implementation. Most of the state-of-the-art neuromorphic chips are asynchronous, and that's kind of why I got involved in this, and that's where we participate. So I thought what I would do is just, very simple level setting. This probably doesn't need to be said for this community, but I figured I would say it anyway, just to be redundant. The word neuromorphic has been sort of repurposed by many groups to mean things that are actually quite different from each other. So I just want to make it clear what I mean. When I say neuromorphic, I'm referring to something that's closer to the origins of the term, which came from sort of neuro plus morphic, which is sort of where the structure resembles what we see in neuroscience, the structure of the underlying circuits and architecture. And as far as this talk is concerned, what that I'm using in terms of neuromorphic is just spiking neural networks, where you have some definition of a neuron that's defined by some sort of mathematical model for what a neuron is supposed to behave like. There's some synapse model, and then there's some connectivity between them, but this connectivity is sparse. Okay, maybe locally dense, but globally it's sparse. And the interactions between the neuron outputs and other things and the synaptic inputs are based on spikes. And just to be clear, what I'm talking about here, these sorts of architectures are not what you would build to implement a traditional artificial neural network accelerator. I'm a digital chip designer. I can tell you that, these architectures don't do a terrible job. They might be better than, say, a CPU, but that's not really a fair comparison. If I had to build an ASIC for, say, doing a deep neural network, traditional artificial neural network, I would not necessarily go down this route. So just to make sure that's clear. So we're just talking about spiking architectures. And if I look at what these architectures look like, you can look at different architectures from different groups, academic or industry, and they kind of all have the standard building block that we call a neurosynaptic core. I should just point out that this is all taken for granted today. This was not taken for granted about a decade ago, but this is sort of the standard textbook view of what a neuromorphic architecture looks like today. You've got some sort of locally dense connections of input axons, or you could think of them as input local dendrites, if you want to think of them that way. You've got depending the axon, at some point the axon turns into the dendrite, and depending on who you talk to, they will argue about terminology. But essentially, you've got input arrivals, you've got local neurons, there's some local potentially dense connectivity, and then there is an output spiking waveform that is then abstracted away into a very simple digital packet that goes out using address event representation that goes to the sort of global packet switch network. Input spikes arrive from a global packet switch network as well, and then get delivered to the appropriate input axons or dendrites, if you like, and that gets delivered to the local neuron, right? So this sort of local sort of compute element, which has a number of neurons and synapses that supports local dense connectivity, that's what I'm referring to as the neurosynaptic core. And then you've got a large-scale system that's an array of these cores. Here I'm showing you a bidirectional mesh network, but that's just the infrastructure you need for communication between from one neurosynaptic core to the other. Okay, so this is sort of what I'm referring to when I think about a large-scale neuromorphic architecture of some form. There are many details up for grabs here, but that's sort of the rough picture I want you to have in your head when I talk about what I mean by neurosynaptic core. Now, so the neuromorphic chip design has a rich history. It started, depending on who you ask, even in the 70s, maybe even earlier than that. But there was a burst of activity in the mid 80s at Caltech, spearheaded by Carver Mead's lab, and the computational neural systems program there that was sort of initiated. And then lots of work on small-scale neuromorphic architectures, and then roughly in the early 90s to mid 90s, people started building larger and larger systems in their own way. I recognize a few of the participants here. Some of them are contributors to this, so you know who you are. So there have been many architectures proposed over the years. And by the way, I got all my degrees from Caltech, so I was a student there where I was seeing all these other groups working on these neuromorphic systems, and I was like, okay, that's kind of cool, but it's not what I'm working on. I work on asynchronous design. And then over time, as their systems started getting more complex, they needed more and more sort of, I call it digital support. Okay, because you might build very interesting analog electronics for local neurons and synaptic dynamics. But once you got to a large scale system, it was fine to have the analog electronics be local, but long range communication, things like that needed digital communication. And to stay in sort of the biologically inspired neuromorphic realm, they wanted all of this to be in continuous time. And if you do continuous time digital electronics, that's my bread and butter, right? So that's kind of how I got involved in these projects, where a lot of the neuromorphic folks who are traditional neuromorphic engineers asked me to help them with their long-range communication problem for neuromorphic architectures. And just so I thought I would show you sort of a few things from from a few sort of historical pictures and microarchitectures that we worked on. So I got involved seriously in neuromorphic architectures around 2007, I would say. Then I got sort of pulled into the DARPA Synapse program, which was led by, was part of the IBM project, which led to the True North architecture. And these is actually a picture from our original proposal, I believe. So that we had submitted thinking, the way we are going to make this scale is we're going to build these axons and dendrites in a dense mesh, dense wiring mesh. We're going to have a 2-terminal synaptic device, which uses new materials. And we were working with IBM research. So every device I've seen in the literature and then some were on the table. IBM has a rich history of research in sophisticated devices. And in around 2008, the main reason there was so much investment at companies like IBM on these devices was to look for a replacement for NAND flash, because they thought it was going to be difficult to scale further. So they needed newer non-volatile memory structures and new materials for non-volatile memory. And that's a big enough market to justify the sort of new material development. And this is what we thought we were going to build. Okay, so when we started the project. So these 2-terminal synapses, which there are lots of papers these days. I mean, this was actually our proposed architecture. And but what ended up happening is it turns out that doing this is not as easy as people would like to believe. And there were lots of problems with scaling the materials, getting good yield, good repeatability, and being able to exploit, say, multiple bits for the synaptic weights in these materials became extremely challenging. And also the utilization of a topology like this, where everything is densely connected, potentially densely connected, is not it's not a great match for what you really want for these neuromorphic architectures, where the connectivity is really sparse. But that's what we started with, and I know that some folks have asked me questions about why we keep calling these crossbars and things like that in those papers. Well, this is why. Okay, we originally thought we were going to build these literally these physical crossbars to implement the synaptic connectivity. So the first thing we tried to do is that, okay, fine, the materials, all that's going to take a while, so let's just build a fully a circuit model for this whole system. And that was the first chip that we built in 2010, which was called Golden Gate. And this is the chip that actually I would argue is the real origin of the neurosynaptic core thing that was being pushed by IBM. And in this particular chip, we actually did have this sort of crossbar architecture, okay, except we had physical neurons and physical neuron for each physical neuron needed in the architecture physical circuit. And then this was truly everything was as sort of activity driven as possible. So the idea was we would have extremely efficient power because only the things that need to switch would switch. And that's actually what we did. So we had physical neurons, we had physical synapses, and then we had the usual input spike demuxing and output spike muxing for address event communication. And then, this is now if you take this as a functional specification, which is digital, which has this sort of time step behavior, then I can implement this however I want. At that point, you can decouple the architecture, the logical architecture from the physical architecture once you have this very, very nice correspondence. And in fact, actually, I would argue that the biggest contribution of this, the work that we did here, is this view that actually you can build these large-scale neuromorphic systems and everything is deterministic, right? And you don't have to have, time-stepped execution to get that efficiency. So you don't need to be clock, as in have all the little local time steps synchronized in time. And the next version of this is we did the true north architecture, where we basically essentially said, okay, we have this logical spec. This spec is this. It turns out that the area here is being dominated by the neuron hardware. You can make the synaptic connectivity matrix very dense by using SRAM. This is all straight digital logic at this point. So we just said, okay, we're going to implement this with make the SRAM take up all the area. Essentially, we're going to have a single neuron data path, and we're going to time multiplex it to support all the neurons. And that's basically, if you take this architecture, decide you're going to time multiplex neurons, and do a die shrink for a feature size, we actually have a direct mapping of how you basically get to the true north architecture. And that's what we did. Okay. So that's great. So my group designs chips, and we're perfectly happy doing that. And so there was a parallel project at IBM where they were trying to figure out how do we try to map applications to this architecture. Okay. And so, we had our head in the, focus on chip design. We had a functional model of the entire chip, a couple of years before we had the silicon. And that functional model was fast enough that you could actually map algorithms to that functional model and see that if they computed what you wanted, okay? And so this was a very nice piece of software developed by IBM Research. I don't know if they ever released it, but it was available internally to the project team, and all the folks developing algorithms for this architecture used that to make sure that the algorithms would run once we got the silicon back. Too many stories here, but anyway, but what the algorithms group converged on, or what they called a core-led programming model. Now, what that means is, so we already said that the entire architecture is subdivided into a lot of little cores. By the way, just to give you some idea, on True North, a core which has 256 neurons, about that core is roughly 0.1 square millimeters of die area. Okay, so so a core is actually pretty cheap from a silicon area perspective. And so they decided that that core would be sort of a unit in their programming model. And any algorithm is going to be specified by saying, I have n cores that I need, and these n cores are interconnected in this way. The neurons and synaptic weights are the following. So in True North, all of the connectivity was static. So you say what all the connectivity is, you say what all the weights you need are, and then you say, here are my input axons and here are my output neurons, and then that's kind of your component in your algorithm. And they call that a corelet, right? So for example, here's a picture from one of the corelet software papers where they say, look, the corelet, it needs 17 cores, and it's got a liquid state machine, and it's got so many inputs, so many outputs with this kind of encoding. And then you got a classifier which has 85 cores, and I just I can hook them up. Sort of if you think about sort of like in MATLAB, you can in one of the toolboxes you can sort of hook components to each other to build a signal processing chain by saying take this output and plug it into this input and so on and so forth, right? So this was what they call the core-led programming model. And my analogy for something like this is sort of like assembly language, right, for neuromorphic hardware, because you pretty much have to, if you're a programmer, if the functionality you want doesn't exist already, this is very difficult, right? You have to now manually figure out exactly what the graph is. You have to be sort of an expert in this neuromorphic architecture, which is very, very different from normal programming where, I can use a microprocessor without knowing anything about the assembly language or the instruction set architecture or how many registers there are and things like that. Whereas this, you needed to know sort of a lot about low-level details. And so even though I have lots of sort of a critique of this, it's not clear that we have a significantly superior solution yet. I'm just going to put that out there. Maybe that's a provocative statement, but there may be one. I just haven't seen it. But I'll talk about a lot of different things that we looked at as programming models. But this was sort of the starting point. This we know how to do. Once you've got correlates and you've hooked them up to each other, now you've got a graph of correlates rather than individual neurons. And then the name of the game is, I have all these correlates. Where on my true north physical chip are they going to be placed? And then that tells me how to program all the routing tables and connectivity for spike communication. Is that clear? Any questions so far?
Throwing to me in the chat.
Okay, great. So after this project, we actually worked on a second sort of neuromorphic architecture project. This was a collaboration with Stanford, Professor Kwaben Abayan's group. Just another, fun fact. We were students at Caltech at the same time and we took similar classes. That's how I know him. So we got to talking, and his group had designed NeuroGrid, which until the True North architecture was built was viewed as one of the sort of the leading edge neuromorphic systems. And he was really excited about this framework called the neural engineering framework. Now, I don't know how many of you, if you're familiar with this or not, I'll summarize it for you in a second. But the idea behind the neural engineering framework is that my target implementation substrate consists of neurons and synapses. That's again the goal. But instead of describing how the neurons and synapses are wired up to each other, instead, what you do is you describe the computation as a system of equations. So, you can say that, y is x plus 3, or y is sine x. You can get very fancy. You can write some sort of mathematical statement that says, here's my input-output relationship. It includes derivatives as well. So you could have basically with that, you can essentially model a dynamical system. Okay, so you can write dynamical systems, got a set of coupled differential equations, if you like. And you've got a time evolution of the dynamics. And the way the neural engineering framework works is it takes every variable in your model and converts each variable into a population of neurons. Okay, and the idea being that the output of this population of neurons is a representation for the current value of the variable. So the time varying output rates of all the neurons in a particular population capture the time varying value of the variable, and the evolution of those of the dynamics of the neurons is going to match the evolution of the dynamical system that you wrote down, right? But sort of fundamentally, this depends on essentially rate coding. So the neuron output firing rate is the instantaneous estimate of the value. It's used to come up with an instantaneous estimate of the value, right? And if you've got spiking neurons, then you need to take the time average of the spike rate, right? So to do this. And they actually, another reason this was appealing is that the group that was pushing this framework has a large number of examples where they've successfully used this framework to capture various properties that they see in psycho-visual experiments and things of this nature. So they're in the cognitive studies department, and they've also looked at data that the experimentalists in the field collect from human beings and things like this, and shown that if they have this model and they map it to these neurons, they kind of they sort of see the same sort of temporal behavior or the same types of errors and things like that. So that was sort of intriguing as well. And they've actually got a very nice software package. It's got a nice visualization framework, all sorts of things called Nengo that they developed. So we started using this. Now, if you're not familiar with NEF, I thought I'll summarize how NEF maps algorithms in this case means a system of differential equations, how it converts this into a collection of neurons. And so the basic intuition is quite simple. So a neuron is simply, a neuron has a collection of inputs. Again, just think rate coding, forget about spikes for the moment. So you've got a neuron, it's got a collection of inputs, you know the current firing rates for all those inputs, and it doesn't care what the neuron is, it's a black box, but it's a map from input firing rates to output firing rates. Okay, sometimes people think about these as tuning curves of neurons and things like that. This terminology is pretty common as well, depending on which body of literature you're looking at. Now, so that's the first basic premise. A neuron is just a map from an input vector to an output vector. Okay, so sorry, single output, right? So input vector to single output. A population of neurons that shares a set of inputs is now a map from an input vector to a set of output vectors, right? So each neuron corresponds to an output vector. Now, so that's the next step. And finally, the value that this population of the neurons represents is the linear combination of the output vector, the elements of the output vector, okay? And the weights of that linear combination are fixed. And those weights are determined by the function you're trying to capture, or the transformation that this pool is doing from that input vector to the output vector. And what this essentially does is, so you've got input vectors coming in, you've got a pool of neurons, and you say, let's say I have a 2D output. I have 100 neurons, and I have an output vector, a value I'm computing. So that takes this 100 neurons, but its output is really one-dimensional, right? That's what it's supposed to be. And then you could have multiple output. You could have a multi-dimensional output, so you could have 2D outputs or 3D output pools. Okay, so that's the basic idea. You can then transform this pool if you like. So you have the value space, which is of some low dimension, of dimension D. And what this does is you've got the output ones, and then those output vectors connect to some other neuron pool, or inputs to the other neuron pool, and that's another set of encoding vectors. And those are typically random. Okay, so that's how the NEF works. And so what this does is, if you take a neuron to neuron connectivity, you've got this map that goes from N to D with a transformation matrix that's D to D, and then D to M for the destination, which is a set of random projection vectors, right? So what you've done is you've taken your N by M matrix, but then you factored it essentially. So you can think of it as basically allowing you to do an SVD on this matrix and only communicate at the D dimension point rather than needing this full weight matrix. So in a normal traditional neural architecture, you would have represented this as an N by M weight matrix, but here you can actually represent it in a factored way. And that was where we wanted to get the savings from. Okay. And so remember I said a neuron is just a map from input vector to outputs. So it's some function, normally, and this is kind of where things like the randomness of neurons, the diversity of neurons you would have in an architecture was viewed as a strength, because if you have more different maps, that increases the diversity of the set of functions you could support with a given neuron pool, right? So in fact, it turns out that there's a very clean mathematical analysis you can do. This assumption that the output is a linear combination is very strong, and it allows you to use a lot of sort of linear algebra type analysis to figure out how sophisticated the mapping that the pool of neurons supports is. Temporal dynamics in the architecture, remember I said you could have derivatives in your model, that's introduced through the synaptic dynamics. But what's really powerful in NEF is if you give me a system of equations, I know exactly what the maps that each neuron pool is supporting, I can compute all the weight matrices from the governing equations, right? So there's no training of the weights, you just compute it. Now the biggest proponent of this architecture is Chris Eliasmith. He was a collaborator on this project, and I would be remiss if I don't say that you can actually support learning in this architecture, but the way learning works is it's going to be a variable in your original model. right? So the learning isn't done by tuning the weights here. The learning is done by changing the representation in the original model. Okay. So this looked all very nice, actually. So, so we wanted to build this architecture where we can take advantage of diversity, so we can support analog neurons, right? The neuron is just a map. I don't care what the map is, because I'm going to I can compute the weights after the fact, and all of this stuff is very nice. So this, we actually spent, I think, almost 5 years working on this project. So this was a collaboration with my group, a group at the Quabena's group at Stanford, and Chris Weissman's group at Waterloo. And we actually built this chip. We called it Raindrop. It was optimized to map NEF networks. And we had pieces of the microarchitecture that correspond to the decomposition I described earlier on how NEF works. So you have input spikes. Those get accumulated. They can be transformed, and they can be encoded, and then they can be mapped to the output. Right? So all of these things, we had microarchitectural structures to support all of these things in Raindrop. And it was way more efficient at mapping NEF networks compared to, say, something like True North or a traditional spiking architecture. And part of that is because we could represent the factored weight matrix explicitly. So in Raindrop, we had direct support for NEF. We could do analog neurons and synapses, and we could do analog diffusers. So this is another design point where we now have going from software all the way to a neuromorphic architecture that we could evaluate. And all of this relies on the sort of the randomness and the stochasticity that's inherent in the analog electronics. And in fact, we had to actually amplify the stochasticity a little bit in some cases. And then we got digital support electronics around it. But so we got a significant improvement in our energy efficiency in this kind of architecture, mapping NEF networks compared to traditional neuromorphic, more than an order of magnitude reduction in energy usage. But we started paying a big price, okay? And the price came from the fact that we were exploiting the stochasticity. So I just want to make this point here because, so this is something we learned, well, we realized this was an issue, and we didn't realize how big an issue it was until a year into the project. Oh, sorry, there's a question, previous slide, arrows. I'm not sure, 1229, maybe this slide, is this the slide? What do the arrows indicate on the connections on the previous slide?
Yes,
so these little arrows,
is Cosme, that's Sandia, sorry. I didn't want to interrupt unless you saw the chat.
No, I saw the chat. Yeah, no, it's fine. Oh, these guys are spikes.
Oh, okay.
Yeah, these guys are spikes, and they have a grade. So we have graded spikes. So that's what Loihi 2 now calls them. But yeah, we have spikes which have some magnitude internally within the core. Yeah.
Thank you.
So some of this is spike encoded. This is sort of digital spike-based communication, and here we actually have an analog distribution at the endpoint. That was actually key to energy efficiency, it turned out, in this architecture. But yeah.
Thank you.
Great. So remember I said the principle in NEF, and when you have a spiking neural network, is we have to represent a value as an average, time average of the spike rate. Oh, sorry, the time, you have to filter the spike train to get the average current value. And because of that, we started, we knew that this was kind of not the world's most efficient way to encode a value, obviously, but we thought there was biological evidence, and there's this nice NEF model, and so on and so forth. And about a year and a half into the project, we said, okay, wait a second, we're paying a high price for this. How bad is it going to be? And so we sat down and did some math, and it turns out that the answer is the price is extremely, extremely high. Okay, high enough that we actually had to do something to avoid to reduce the spike rate dramatically, at least for global communication. And the analysis we did is quite straightforward. So supposing I want to send some value with some precision, so some number of bits of precision from a sender to a receiver, right? So I'm going to say I have B bits of precision if my maximum error is 2 to the minus b plus 1, right? So this is, if you're used to numerical analysis, this is a half ULP error, or error is 1/2 units in the last race, right? So that's the standard sort of view of what b bits of precision means. And here I'm assuming absolute error, not relative error. So the sender wants to send a value v, the receiver gets a value v hat, and I need the error to be bounded by epsilon. But now I am doing a stochastic model, right? So I'm doing these Poisson spikes, and I'm going to take the time average of my point, whether a spike occurred or not, to figure out what the value I'm trying to represent is, right? So if there are many, many spikes, then the value is closer to 1. If there are no spikes, the value is 0, right? That's pretty straightforward. It's just doing time averaging. Now, if it's truly stochastic, then the problem is that you need a second ingredient to see how many spikes you need. Because there is some non-zero, even if it's incredibly small, there is a non-zero probability that your coin tosses will be so bad that you get the wrong value, right? So let me take a very simple example. If I want to send the value 0.5, I want roughly half the time I want a 1 and a spike, and half the time I don't want a spike. But if I do this by coin tossing, then I might toss a coin and always not send a spike, even though I have an unbiased coin, right? You might just get really unlucky. So the second parameter that we added to the analysis is this notion of confidence, or how confident are you that you get the correct answer? So we have epsilon that says the precision I care about, and then you've got delta, that's my confidence. So you want the probability of the received value violating your error threshold to be less than or equal to delta, right? That's the idea. And then the question you ask is, okay, if I want 1 bit of precision and I want 10% confidence, I want 90% confidence, so delta is 0.1. How many sort of time slots do I need to average over to guarantee that this will be true? And it turns out this number explodes. Okay, so this is the calculation for Poisson distribution. I make a simplifying assumption about the tail. If people are interested, I'm happy to get into how I got this calculation, but I'm happy to take that offline probably. But what you'll see is that even if you have you need a few bits of precision, the number of time slots you need is incredibly high. Okay, and even if those time slots were silent, I'm still burning power in my architecture for this time window. And so once you start looking at this, you basically very quickly realize that actually this is going to be very expensive. And so to fix this problem, there's actually another very nice way to look at the same picture. By the way, the scaling of this is e to the n squared. Okay, so where n is the number, e to the epsilon squared, where epsilon is the number of bits of precision. Okay, it's pretty bad. But that's fine. We all know that the scaling is going to be bad. But it turns out that even for a small number of bits, it's bad. And that was sort of the bigger surprise. And by the way, we discovered this, we first realized how bad it was going to be because we actually tried to build a real application using the NEF and spiking neural networks. And then we were like, wait a second, this is not going to work at all. And then we sat down and did the analysis to figure out why. Another nice way to view this data is the following. So here n is the number of time slots over which I average. Okay, so each n here is another order of magnitude. So it's 10, 100, 1,000, 10,000 time slots, right? 1,000 time slots, that seems like a lot, right? You would say, oh, that should give you like 8, 9 bits of precision. But that's this blue curve here. Okay. And this is how many bits of precision you get at a particular failure probability, right? So, for a particular failure probability, even failure probability that's not that high, I'm already at 4 bits of precision, right? So if you care about the answer with a reasonably high confidence, you're in trouble basically very quickly. You need it becomes very, very expensive to do this. Okay, so we did this project, and in fact, so the way we tried to mitigate this issue, is this consistent with the central limit? Absolutely. The asymptotics are completely consistent with the central limit theorem. In fact, I would argue that the only interesting thing, by the way, if you want the main inequality you need is Hufting. I'm sure you're familiar with that. So Gert was asking, is this consistent with central limit? Absolutely. You just need a Hufting's inequality to prove this, prove the scaling law. It's pretty straightforward. So scaling laws, that was kind of obvious a long time ago, I think. But what was surprising is what the actual numbers look like for low bits of precision. That was what was surprising, that how bad it was. Okay. So, so this is we have this very nice general framework to map an algorithm to a substrate, and it's got these really properties that make it very, very difficult to use. So then you do what we did to mitigate this, by the way, is we had internal digital thinning of the spiking. So we sent essentially spikes that had more than 1 bit of value. And we did that by internally doing digital accumulation of spikes. So we would filter the spike train. And there's some very nice analysis done by one of Quabena's students, Sam Folk, which talks exactly about the optimal way you should do this accumulation to minimize the global communication traffic. And that's what we did in BrainDrop. By the way, without doing that, we would not be competitive with True North, I would argue. Okay. But after we did that, we were much better. But still, the scaling is still going to kill us eventually. So the question is now, what next? And so we had these sort of systematic ways to look at algorithms, and now we're in the realm of looking at what other people have done in the algorithm space. And over the past sort of year or two, we spent quite a bit of time looking at what people have been doing, mapping different techniques to the neuromorphic underlying substrates. And we looked at a number of different sort of handcrafted networks, is the way I would describe it, which can be used to map different types of algorithms to a neuromorphic architecture. And I'm showing you sort of 3 examples. But we looked at least over a dozen or maybe even 24 papers where they said, we do this with this neuromorphic algorithm and we get much better performance than a CPU, GPU, a conventional way of doing it. So, and every algorithm we looked at, I hate to say this, but I could put a little asterisk and say, yes, but. And the buts started bothering us, okay? And the buts would be of the form, yes, that's great, except, it works for this value of n, but if I double n, all of a sudden it's going to fall apart. Or, yes, there is this neuromorphic piece, but then I need this global view of the network that I have to scan to extract all the data to figure out what my answer is. Or, yes, this works, but your competition, the software algorithm, has this incredible degree of generality that you cannot support at all with your neuromorphic architecture. And so if I change the problem by epsilon, your approach doesn't work, but the software algorithm is still just as good. So there's a lot of brittleness in these comparisons. So we were trying to come up with a way to do this to be fair about our evaluation, right? So I mean, I'll give you a very simple example. Let's just take sorting, right? So there are papers on neuromorphic sorting, and they make certain assumptions. Now, it turns out that with the same assumptions made in the neuromorphic sorting papers, I can build a linear time sorting algorithm, right? I don't need to use merge sort or quick sort or an n log n algorithm, which was their baseline comparison. I can actually do it in linear time, making the same assumptions that were needed for the neuromorphic architecture to work. And there's just zero, there's no chance that the neuromorphic architecture is going to beat it. Not only is my algorithm linear time, but it's actually embarrassingly parallel. If I don't run it on a parallel architecture, it's log n time. So anyway, so there were things like that. So, so we found these sort of, for better or for worse, I have a computer science background. We took lots of algorithms courses. So there are lots of gotchas in just even algorithm complexity analysis, where once you start depending on things like the value of the input data, all of a sudden things can be changed dramatically if you're not careful. So we decided that we're going to try to do this sort of a systematic analysis. So we wanted to have a systematic way to take some sort of neuromorphic algorithm, have some substrate we can use for the neuromorphic architecture that was realistic, and then do a mapping in a way that was not, I didn't rely on my expert knowledge. And then sort of, can we do a comparison? And that's what we've been working towards. And I'm going to use my remaining time to talk about what we've been trying to do in this space. And we more than welcome collaborations. So, so how do we do this evaluation in a fair fashion? So I'm going to claim that we are trying to build a neutral hardware and software stack. So I put a little asterisk on neutral, right? Nothing is ever neutral. This is includes all my personal biases. So just going to put that out there. But the important thing that we wanted an architecture that has enough detail to capture a realistic large-scale neuromorphic substrate. One of the problems that we found is, well, okay, first of all, there are the evaluations that say just use Louis or something like that. So that's great, right? That's pretty clean. But people who had sort of a new neuromorphic architecture, they were using, say, one core to come up with energy estimates for what the overall algorithm would do. And we found that, just having built now 3 different neuromorphic chips, the gap between one core and the entire chip is a huge factor. So it became very so we wanted there to be a realistic substrate. And the other thing we wanted to be able to do is put this out there, so like other people can use the framework or things like that. Tell us what we did wrong. So the approach we've been taking here is we have our own hardware description framework for asynchronous design called ACT. It's actually open source. It's on GitHub. This was actually funded by DARPA to build an ASIC flow for asynchronous design, since one doesn't exist. So this is the first ASIC flow ever developed for asynchronous circuits. This is something my group worked on for about the last 5 years. But what's interesting from a neuromorphic architecture perspective is my behavioral description is a message passing programming language. Okay, so those of you used to programming parallel machines, this will look very familiar to you. Those of you who are used to writing Verilog, this is going to be very odd. So just to be clear. But we actually have a complete implementation of something that is roughly, I'll call it like Loihi class neuromorphic architecture. And it's about 2,000 lines, 2.1K lines. This includes like white space and comments and, squiggly braces and things like this. Okay, and just a raw word count. Okay. What's nice is we've got a sort of microarchitecture of the full neuromorphic system. We've got the router. The router has pipeline stages. I mean, it's pretty detailed. And we can map this to an ASIC. We can map this to an FPGA. We have an FPGA prototype of this running. It's no problem. Okay, and so we can, you can run it on hardware. Even, we will, once we are happy with the architecture, we will probably tape out a chip as well, make sure it works, and make that available if we can. That's the idea. The key conceptual difference that allows us. So, by the way, for those of you who built a chip, 2.1K lines for something like I call it a couple hundred core neuromorphic architecture is very little. Okay, just for calibration. So I have I only have like 15 minutes left. So instead, I'm not going to get into the details of how ACT works, but it's basically, think of it as I have a parallel programming model of the overall architecture. I'm not going to get into the language. So I'll just talk about what the architecture really looks like. So we've got a bidirectional mesh. We've got bristled cores. Each core has 4 endpoints. By the way, this is kind of very standard. If you've ever built a chip, this is pretty much textbook. We've got distributed. The core itself has a dendritic memory. It has support for learning. It's got a local timekeeper that advances the global time step. It's got neuron memory. It's got a routing table, and essentially there's a compute pipeline. And the way this essentially works is, at a particular time step, you scan through the local neuron memory, you update the local state, you grab the current dendritic inputs, you compute the new outputs, and you send out output spikes. And this is all asynchronous, so you just send the messages and the spikes get delivered. The spikes go out, and then once you send say there's a spike that's generated in this core, eventually it's going to get routed out to the destination core, arrive in the input dendritic memory. And this all happens asynchronously in continuous time. And then eventually time advances and the neuron state is updated with the new dendritic information, right? So that's roughly how it works. And I just wanted to show you, this is literally from the model. This is the neuron update, okay? And most of it is extracting bit manipulation, okay? So you get the neuron data, you read the current neuron state. It turns out the neurons there are a number of parameterized models that can be configured. You update the leak, you do a neuron update, and then you update that state, and then you go to the next neuron. And this is an infinite loop. This is literally the description. This gets automatically translated into hardware, right? Don't like the model, you can change these lines and do whatever you want, right? That's the idea. In fact, we're talking to some neuroscientists, and the reason they're excited about this is that they can change the model, right? And it's fine, and we can prototype it on an FPGA, so they're not going to really lose a huge amount of performance if they have a fancier neuron model, for example, that they want, right? The internals of the core microarchitecture is essentially you've got an input spike, input axon table, you've got dendritic accumulation memories. There's a learning unit that can support pre before post and post before pre. We support gated synapses. There's a bunch of features that we support. And all of this is all of the programming, the configuration of the entire architecture is controlled by memories that you can program from off-chip. Each neuron has associated with it a spike record, so you can then check if it spiked in the previous time step, it is spiked in the current time step, things of that nature, and use that for the learning update. Can ACT be translated into another HDL like Verilog to be implemented in an ordinary FPGA? Yes. That's in fact exactly how we map to an FPGA. We take, there's no reason to reinvent the wheel. So what we did was we took the ACT hardware description and we generate synthesizable RTL that you can map to the FPGA. And then we use the commercial FPGA tools to map it to the FPGA architecture. Absolutely, that's how we do it. Okay. Does the architecture support stochastic state variables with internal RNGs? Yes, we have a branch that does. Yes, you can do that if you want. Yeah, so we have support for that. The RNG right now is just a simple linear feedback shift register, but again, the nice thing is you can change it to whatever you want. Yeah, you can have stochastic state variables if you like. Yeah. These are actually, believe it or not, these are relatively straightforward changes. The more complex thing in the whole architecture is getting all the synchronization right to have a deterministic execution model and make sure all the neurons are time-stepped correctly and so on and so forth. But that infrastructure doesn't have to be changed. Okay. Any other questions? Okay, so I'll give you a rough idea of what's happening on the hardware side. So let me talk about what's happening on the software end. Remember, I wanted to be able to evaluate algorithms on neuromorphic hardware. So this is going to be my hardware platform that I'm going to use. Oh, by the way, I didn't say this, but this is massively parameterized. So you can change the number of cores, you can change the size of the axon table, you can change the size of the dendritic accumulation tables, you can change how much axonal delay you support. So here I'm showing you a picture with 2 dendritic accumulation tables, so times t and t+1, but you can have this up to t plus k, where k is a parameter. There's, how many bits you want for the neuron, the current neuron membrane potential, for leaks, for weights, all of these are parameters in the model, okay? So this is all parameterized. So I should just make that clear. Because part of what we want to do is explore, what's a good architecture with this approach. Now, I'm going to switch gears to software mapping. So we are starting to use Fugu as our front end. So we were initially just saying we have some sort of neuron graph of neurons and synapses with some parameters. And then we were talking to Brad and a few others at Sandia a few months ago. And they talked to us about their Fugu framework. It's like, okay, we can just use that. That's great. Given that if there's a group that's actively using it and maintaining it, then that's fantastic. So let's just do that. There's no reason to reinvent the wheel. So we use Fugu as our front end at the moment, and we've just got this piece of this software flow working as of like last week. Okay, so what we do is we use Fugu to build our network. We have bricks of various kinds that we've defined ourselves. and we can hook up the bricks, and then lay the bricks, as and do all that stuff with using Fugu. And then at the end, we have a network X graph. So the first thing we need to do is we need to take the network X graph of neurons and synapses and figure out how should we cluster these neurons. So what neurons have high dense connectivity that we should group them together. and we do this through a min-cut hypergraph partitioner that we have. So we group neurons into clusters with a hypergraph partitioner. And then once we've done that, then we have a second graph that has clusters of neurons. And we know how many connections are between the neurons. And so we want to put clusters that communicate heavily next to each other in the architecture. And the way there's a very storied collection of history of research in this space, and it's used for VLSI chip design. Remember I said the ACT flow was developed as an ASIC flow. So we have hypergraph partitioners, we have state-of-the-art placer code that we just repurpose for this. So we use a VLSI placer that we developed. The cost function is going to be different here, but that's all. That's just a parameter. And we can basically take the network X graph, color, if you like, the neurons to group them into clusters, and then place the clusters to minimize communication costs. By the way, I should just tell you that in TrueNorth, there's a core net programming model, so there's no clustering phase. But the placement was, in fact, exactly done this way. In fact, I remember I was talking to some of the IBM folks at Almaden about, they were like, okay, how do we do this? I was like, you should call this person at IBM Research, and they have the state-of-the-art placer, and you can just use it. And that's what we did. This is no different. We can just use standard ASIC placer with appropriate adjusted cost model. Once we have this placement, then we can build a very detailed JSON file. We use JSON just because it's easy to read, and parsers in every language imaginable. So we have a JSON file where you can say, this is a core, here's the axon mapping, here are the neuron mapping, here are the remote core tables, here are the neuron models that you have, et cetera, et cetera. So we can now auto-generate this JSON file that places all the neurons and all the different cores based on the algorithms I just described. And then we have a tool that will take this JSON file and generate memory programming packets, which is basically what are the off-chip packets that you need to send into the chip to program all the memories and set all the internal states before you start execution. So that's all done, that's all working. And then you can just run everything either on an FPGA or actually in our ACT simulator. So that's the evaluation platform that we've developed. And so we've got bricks for various things. I just talked to my students this morning. We now have bricks to do things like graph search, and we should have a brick to do lasso, by next week, things of that nature. So we're trying to sort of reuse work that other people have done, and also hopefully use this as well. Pretty much out of time. So I just want to say that there's actually still a huge amount of work to be done in understanding algorithms and how they map to neuromorphic substrates and what works well and what doesn't. And we're trying to develop a framework where we can study this in a sort of a systematic way, right? So something that I can give you, you can run it and say, yes, I get the same answers, right? Something that I don't have to sign an NDA for, things like that, where we can collaborate. It's easy to work. My funny story about TrueNorth is at some point I got so tired, I returned all the TrueNorth hardware I had to IBM, even though my group designed a lot of the hardware, because it was just too painful to keep track of all the requirements. So we are trying to keep this as open as possible. We're trying to develop a framework we can study this systematically and hopefully reuse framework that folks at Sandia have been building as well. And we're hoping that people will share and contribute to this sort of infrastructure, and with the hope that we have a better understanding of how neuromorphic systems really work and what they're good for. So with that, I'll stop, and I'm happy to take questions.
So thank you so much.